Hi all, welcome to Theoretically Podcasting. I'm joined today by Amr. Hello, Amr.
Hello. Hi, Basu.
So Amr is now a postdoc at the University of Cambridge, and he has kindly agreed to teach me and hopefully some of you about sigma models, the C theorem, the local renormalization group, and at some point, off-shell string theory. So today will be, I guess, the first episode of the Sigma Model Chronicles, as we can call it. And yeah,
Okay.
so I'll have you take over then, Amr.
Well, thank you, Basu. I appreciate it. This is exciting. Thank you for the opportunity to explain a little bit about this exciting research that Erin and I have been working on for the last couple of years, basically. And we just recently have two publications out, and we probably perhaps more in the recent future
Yes.
about off-shell string theory and in general what off-shell string theory is important for in the general. Why do we care about it? Why do we care about learning all these subtleties, and what is it important for? And as we say, especially in the in version 2 of the paper, if my goal from this, my grand motivation from learning off-shell string theory is to bring it into the bulk of
Mm-hmm.
ADS-CFD. So consider the bulk of ADS in holographic setup, basically. Consider the bulk to be an off-shell string theory and ask
Yes.
different questions. That's what I want. That's what I'm hoping this formalism will allow me to do. And there's several questions that are important, and I think that will require off-shell string that will only be answered within the formalism, the framework of off-shell string theory. And one of the questions, so I want to be able to make some statements about the recent, well, not only the recent, but the developments that have been going on, I think recently in the last 15, 20 years in semi-classical gravity, starting from
Mm-hmm.
the RT formula and the HRT formula and the firewall paradox and the entanglement wedge reconstructions and this bulk dualities and bulk subregion dualities and these kinds of things and page curves and information paradox and these kinds of interesting developments, but I want them to bring these kinds of things to the realm of string theory. We often forget that with holography, that maybe the one, which I think I would say the only one, correct me if I'm wrong, concrete realization of holography comes from string theory back in 1997 or something, and it was for super Yang, right? This is the most concrete realization. So if we're gonna we have some well-defined theory of quantum gravity called string theory, and the whole point of this is to try to make some more concrete statements or realizations of these concepts like the RT formula and in string theory in the bulk. And what you realize immediately is that you will need to define it in string theory in backgrounds that
Yes.
are not that do not correspond to conformal field theories, as usually is a standard lore. And so if you want to make a statement about the RT formula, if you want to derive it or do a path integral direct proof of the RT formula, for example, a la Malthusena, right? If you want to just blindly go through the derivation or the steps of the derivation, for example, and say, okay, I want to reincarnate these steps in string theory, you realize that you have a stumbling block, and block is you don't know what it means to go away from the saddle point that solves the Einstein gravity or the gravitational Euclidean action. Okay, that basically means you want to go off shell and define some formalism that defines string theory away from the conformal field theory, right? And if you want to make statements something about ER equals EPR, again, it's RT formula, and you want to ask different questions that will definitely lead you to consider string theory in these kinds of off-shell contexts. There are many other things many other questions that one can ask, And this is the grand motivation of learning this formalism and extending it. There's many extensions that we still have to do. And Lorentzian signature, time-dependent backgrounds, many other extensions. So the formalism, the one will be forced to actually implement before we get to the exciting applications that I just mentioned in a holographic context.
Definitely. Well, I mean, that's also what makes me very sympathetic towards this. And to add another angle, there's a lot of questions to be sort of delineated from the first principle standpoint, having to do with getting a bulk positive cosmological constant as well. And the context in which that's well understood is in the context of doing some string compactifications. Whereas there's these new models that I've been involved with involving, extensions of the ADS-CFT that we're trying to bridge in some sense to these string compactifications. But essentially, you need knowledge of the off-shell formalism to a certain degree of precision to be able to make these connections precise, to be able to work with them in any sense. And there's a lot that's quite interesting. And I mean, the connections are quite striking. For instance, the basic connection, which we'll go over between renormalization group flow and bulk or target gravitational dynamics. There's a sort of very neat way in which two-dimensional renormalization group flow, as we'll see, is connected, or rather the fixed point condition for the renormalization group flow is manifests itself as target space Einstein equations. But there's also another sense in holography that, like, just radial evolution, which are certain components of the Einstein equations in the bulk, are the boundary renormalization group flow of your dual theory. And also the fact that gravitational action on shell from the ADS-CFT perspective and in any sort of holographic perspective with non-zero cosmological constant is just given by measure of proper space-time volume. Even if you put in some Dirichlet walls, whatever you do, there's just proper space-time volume by construction is always the action on shell in the bulk.
Yes.
But it's
ADS5 plus S5 is usually
exactly, yeah. But you see, the fascinating thing is, as we will discover, there's a sort of very interesting role to be played by the volume in a slightly different sense here too, when you think about it from the sigma model perspective. And so there's these very sort of enticing connections. But to put these two things together, I mean, this was something that I thought I could do during my PhD. Of course, I was very ambitious and very conceited. I didn't come anywhere close. But
it's always okay to be ambitious.
But I mean, I think that it's, I mean, our careers are not over yet. We have time to do it. So I'm very excited very excited to learn. And yeah, so I think that this is this is like the sort of podcast I was waiting to do. I've been waiting to do.
Absolutely, my pleasure. I hope it's useful. I hope that we all learn together.
Definitely,
because this is also going to be a learning process for me as I try to explain all these intricate concepts in some way that I hope is I don't get to actually the time to do during talks.
Of course,
and before they get into the weeds. But yeah, so. So I think the starting point, as you can see on the screen, definitely Graham Shore is not me. It's not my name. So, but I thought that I wanted to start slowly building up to the off-shell formalism, and I'm going to take a certain route here. And I'll start from the basics of C theorem and beta functions and in 2 dimensions, because this is most relevant to the 2-dimensional worldsheet sigma model RG flow that is at the central fundamental building block of the off-shell formalism. And so I'm going to start with this and then start with the and explain the logic of C theorem in two dimensions, which you explained before, as you've just told me in your previous podcast. You went through it. I'll go through it again.
Good.
Maybe
Yeah.
try to highlight the important ingredients that will be generalized in the off-shell formalism, right? And keep in mind that this is two-dimensional space-time, but when we go to string theory, this is going to be a two-dimensional world sheet. So, which is not the space-time, it's just some world sheet, but you'll see the equivalence and between the two, and this is just a version which does not have the string theory subtleties on top, does not have the nonlinear sigma model on top, and so the dilitons and all these guys. So this is the central building block. We explain it, and then maybe some other time we generalize to the world sheet sigma model and see what the intricacies are involved or the intricacies involved are.
Sure, sure. Yeah, well, it's nice because here you're covering Shore's paper, whereas last time I covered Osborne's paper. So we have sort of covered, we're sort of, picking up almost where we left off last time. So
Absolutely,
please proceed.
fantastic.
Yeah.
Thank you so much. This is. I'm not gonna, let me spend here just a few minutes on scale conformal vital invariance. This will also at least be important at some point. So let us start with the statement of scale conformal and vital invariance. As you know very well, that the Lorentz group for massless particles in 4 dimensions is the conformal group, SO2, 4. And here we talk specifically, of course, for 4 dimensions. Usually it's SO2, D in 2 dimensions. It has 15 different generators, Lorentz transformations, rotations, translations, special conformal transformations, and the most important of which, at least to me and the beloved to my heart, dilatations. That's the always very special. And then here is the commutation relations that define the symmetry of the group, the generators of the group, standard stuff. And notice that if you have a global scale invariant theory, a global here simply means that your scale parameter is basically not position dependent. So that's just a constant, basically, is what I mean by global in this context. You have extra generators between the Lorentz transformation and the dilaton, and similarly for the translations. And similarly, of course, you have the special conformal transformations, K sigma. So then, this is probably very basic stuff. The important thing is to notice that the algebra that has only J mu nu, P sigma, and D, P rho and D, it closes on itself on the semi-direct product SO1, 3 cross R. So in principle, what this shows you is that a theory can be scale invariant, but it doesn't have to be conformal invariant. It has to have the conformal group. Of course, this reminds me of the famous paper, I think, not sure, blanking on the author's name, that scale invariance implies conformal invariance in 2D, right? So that we can talk about this maybe in this context later on, but let's move on. Here, the important thing at this point is that we know that for every symmetry, there's a conserved charge and conserved current, and the one that I really is going to be important for us is the conservation, at least in the context of the 2DC theorem, the Smolodchikov, is the conservation of the express energy tensor or the energy momentum tensor. This is the statement that the charge is conserved, or the current is conserved. And then we also have the notion of global scale transformations, and we basically the stress energy tensor T mu nu is usually expressed as a total derivative, also in current, and this is explained in the in chapter 5 in the yellow book. It is more detailed. We conserve this current because scale invariance is not a typical Nether's current, so it's kind of subtle, and you know the difference between this and other currents, and so there's a way to construct it, and basically the T mu nu has this form of a total derivative of this what we call virial current, Again, this is not something important, just going through very basic stuff. But let's suppose this is all in flat space-time. Now we want to go to curved space-time and define the energy momentum tensor in this way. This is a standard definition of energy momentum tensor as the functional derivative of some action S with respect to the metric itself. So far, we're just not talking string theory. We have just a space-time. And then the diffeomorphism invariance is basically the covariant derivative of it vanishes. This is the statement that it's covariantly conserved. Similarly, if we have Weyl transformations, then we have this omega squared g mu nu. And again, omega of x is e to the sigma of x. Global Weyl transformations. Global, again, as I mentioned before, means that the scale invariant, the scale parameter, scaling factor is constant, does not depend on x. And then you get that the action is going to be an invariant if the Lagrangian transforms T mu nu is basically the covariant derivative of this current V mu. Okay, now let's focus on the important thing. Suppose now we're talking about local scale invariance, and this is something that we're going to remain with us from now on. We're going to be interested in local Weyl invariance, which basically means that your sigma of x is a function of x. So that means that your scale parameter is always a function of space and time x, and you scale the metric like this. Then, if you start, for example, with the Lagrangian of a massless field, right, some CFT, and then you do an infinitesimal scale transformation, you find that it is going to delta G mu nu would be something like, so if you do like this, delta G mu nu would be something like 2 sigma x, all right? G mu nu
times G. Times G.
Times G, of course, G mu nu.
Right.
Thank you. And then if you plug this into the Lagrangian, for example, let's say a momentum massless field, you find, and you vary the Lagrangian, you find that the condition for being an invariant under this transformation is that this guy, the trace of the stress energy tensor is 0, strictly 0. And
right.
then now try to quantize. Now try to compute the effective action, right? Try to compute the effective action. Again, you can do z example equal e to the minus w, and this will be the effective action. This is this thing, and you do go through the derivation again, go to the variation of the effective action in this case. You find that the Weyl invariance is broken. There's a Weyl anomaly. The Weyl symmetry is broken locally, and that the stress energy tensor has this nice form of the central charge. We're talking here about massless bosons, basically just C over 24, for example, well, in general, but if it's going to be, for example, a massless boson, be like 1 per 24 pi times R.
Yes.
And in the appendix of the yellow book, appendix 5A of the yellow book, it has a very nice exposition of the T mu nu computation of this thing. Very nice, very nice. And you'll see, and why is that? So because, of course, when you go to curved space-time, when you quantize and you go to curved space-time, the Weyl, there's an extra scale, which is the scale of the curve, which is basically the curved space. Because it's curved, that means there's this intrinsic scale. And this intrinsic scale breaks scale invariance at the quantum level. And this is what's happening. And this is the reason why you see that the trace of this trace of the stress energy tensor has the Ricci scalar in it. The Ricci scalar, right, is a measurement of the intrinsic length scale of your curved spacetime. And so you see that if you're not in curved spacetime, this will be 0, and this will you'll have a Weyl symmetry, you'll not have Weyl anomaly. So that's also the reason why. Okay, so this is basic stuff so far. But this is important. So the statement that T mu nu has a central charge in front of it times R, and this central charge can be n, right? It measures some degrees of freedom. That could be anything. Here is going. Okay, good. So this is very basic. Again, I'm not going to make a big deal out of it, but just thought to start very slowly. Now we get to the renormalization group flow and the Zamolodchikov C theorem, right? It's really one of the, I consider one of the striking theorems in RG flows. The statement here that basically tells you that it gives you an information about theories, right? Different theories. One of them is the UV, IR. It tells you how they're related in terms of their field content, in terms of their central charge, which is basically reflected in the central charge as you flow from one to the other. And it's very powerful, as we're going to see, because it basically gives you some constraints, if you will, on the kinds of theories that can appear in a specific RG flow, right? Not any theory that has to have some constraints to be able to satisfy the Zamolodchikov C theorem. And let's important to point out that the Zamolodchikov C theorem applies only to Lorentz invariant theorems. Lorentz invariant is important. Unitary conformal field, quantum field theories, and for which there is a conserved stress energy tensor, right? Denoted by the fact that there's a covariant derivative acting on the stress energy tensor. See, these are the main assumptions of the Zamolodchikov C theorem. And again, this is in flat space. So because this is going to be very important when we generalize this to curved space, this is flat space. Okay. So everything here is flat space. So you'll see that when we get to the off-shell string theory, for example, and try to do this on a sphere, things are not as easy as it is here. Break down, and there's lots of subtleties. But it's important to point that out here. Okay, good. So start with an interacting field theory in 2 dimensions. Simple. Just give you some theory, some Lagrangian fields, and some interactions. Interactions come with coupling. Cool. They're couplings. Okay. And okay, so if they come with couplings, the question is, there's going to be flow. They're couplings. Couplings are, as we learn in renormalization group basics, they're functions of a particular scale in your theory, RG scale, right? And therefore, as you change the scale, theory flows. Flows to what? Where does it go to? This is a very rudimentary explanation of RG scale. There's lots of subtleties that we can get into, but the point is I have an interacting field theory in 2 dimensions, and there are couplings in the theory. Here in the Zamolodchikov, they're taken to be infinite number of couplings. They're infinite number of couplings, and they will sort in RG kind of sense. And then I take them, and then flows. And the question is, where does the flow stop? Does it stop at any point? What does it mean, stop, right? Stop means it actually has a fixed point. So something like, so if I start from something like this, I start my UV theory here, and I flow to an IR theory here, right? Does the flow, so this is a particular theory in the UV, and I flow in the IR. Does it even stop? Or does it keep going? I mean, there's a scenario where it can keeps going and going and going. There's no point. It is no point where I consider this an IR point. And this is what we call sometimes the CFT, because it's a conformal field theory. So as I change the scale, at each point is along this RG trajectory. There's an RG trajectory right here. This is RG trajectory. As I flow, I keep changing my scale. So this is, I define a particular scale, let's say mu, and I keep tuning mu and changing mu as I flow. To the IR means longer wavelengths, smaller energy scales. As each point along here means mu is being changed. And what happens is that at the fixed point, I change mu, and I find that the theory is basically not changing anymore. That my couplings in the theory, my correlation are not basically changing as I change mu anymore. And this is what I call a fixed point. It's fixed because my coupling constants are not of my interacting field theory are not changing anymore as I change the scale, right? And then I call this a fixed point, and it's usually a conformal field theory, right? And this is something that is this is basically the basic picture. So no matter what the details are, it's a basic picture. You have some function, you have some UV theory, and then you start flowing. Flowing means basically changing the couplings. Any flow of an interacting field theory is generated by beta functions. Right? The generators are beta functions. Whenever you have the beta functions are not zero, means they generate the flow. When the flow stops at a fixed point, that means the beta functions vanish. So it's so easy. So it's really what this is really the
Right.
picture. Right? And so
Yeah, so I guess in a sense what we should be saying here is that on the space of couplings,
yes,
the move of rescaling is actually generating a vector field.
yes,
And what we're looking for are integral curves of that vector field that have some finite length. You know, they begin and end at fixed points. And basically what we do is try and look at what the velocity along these integral curves are, and that's what the beta
yes,
functions are giving us. And
exactly.
so the sense in which we say that usually beta functions vanishing puts us as at a fixed point is just saying that, you know, you stop there. There's no velocity anymore. Which have some first order system.
That's a very nice way of putting it. There's no velocity anymore in the flow. And remember that here we're always going to be talking about space-time and RG space. So there's a space,
Yes,
there's
yes.
the actual physical space, but you're always going to see people talking about RG space and metric on an RG space. So please do not get this confused with basically the actual physical metric on the physical space time, right?
Right,
Um,
right.
Good. It's just important because, you know, if
And we're going
again,
to make use of both eventually.
absolutely true.
And of the
Absolutely,
crucially important insight to string theory is that.
absolutely true. Exactly. Absolutely. Um, Good. So let's start and see what the C theorem is, the two-dimensional C theorem is. And here is maybe the starting point of well, there's some okay. So here we work in a two-dimensional Euclidean space. So we work in a two-dimensional Euclidean space, and then we choose some complex coordinates, z bar is x1 plus ix2, and therefore this is simple algebra to show that the conservation equation of the stress energy tensor, which we explained as a consequence of the translation symmetry, is going to take this form.
Yes.
The del z bar tzz, the tzz component, plus 4 del z tz z bar equal to 0, right? This is basically equivalent in what we explained up there to del mu d mu. Okay, good.
Yes, yes.
Now, I would like to construct, I would like to construct a function. This is a lot of intuition here, okay? So you can ask me how, okay? Well, there's a lot of intuition here. That there's no just one algorithm that can give you, here's how you construct this function. It's not like this. Again, and then for example, for the holographic proof of the C theorem, again, there's some intuition that went into the construction of the monotonic function.
Yes, yes.
Um, and it's so again, intuition is intuition. Here, what you want to construct a function z. By the way, the couplings are referred to as g. That monotonically decreases along the trajectory from uv to the ir. So you want to construct a function at the uv where, and then it keeps, the function keeps decreasing all the way until it gets to an IR, and this function is going to be equal to the central charge of the CFT fixed point at the IR. Okay, and so this is basically the statement, and you find that CIR is, well, we'll get to that. let's see what Simological did. And if you read the original paper by Simological, you'll not find any insight into how he thought about constructing. And I trust me, I did try to find some insight into how he actually, what he was thinking when he constructed this F, H, and G. But anyway, he is Simological after all. So, so here's the thing. He constructed three functions, f, h, and g, as 2-point functions of different components of the stress energy tensor. So we said that the stress energy tensor has TZZ, TZ bar, Z bar, TZ, Z bar, right, good. And constructed these functions, and we have, because of UV short distance physics, we have these coefficients that appear right here because of the OP coefficients. I mean, these are known stuff. And then notice that, and this is important, notice that the H, especially the G, let me even draw that. The G has the TZ bar, TZ bar. That is 2-point function of the trace.
Yes,
okay?
Yes.
It's very important that this is, so I can maybe write this as Z squared, Z bar squared, and this is T mu nu x, T mu nu 0. So this is 2-point function of the trace. Okay. So remember that our statement of Weyl invariance, local scale invariance, which I will call Weyl invariance, is the vanishing of T mu nu, right? Vanishing of T mu nu. And that's important. So whenever I'm a fixed point where I don't have any scale in the theory, so conformal field theory, I don't have any, the T mu nu will vanish. Remember, this is what we started with, right? This is the point. And here, there is a point here that if you have marginal couplings in your Lagrangian, which is also something that was in the sum logical C theorem, then you can definitely, you can express your T mu nu as a sum over the couplings, your operators OI, response to couplings, and your beta functions associated with them. So for each coupling that you have in the theory, for each operator that you have in the theory, you have a particular beta function that defines the flow, right? Defines the flow. And we'll come right now to the definition of what the beta function is and how it encodes the RG flow, or the scale information about each particular coupling, right? Here, always a renormalized composite operator. We'll get to that, I promise, at some point. We'll define composite operators and what it means. But the point is, look at the trace of the stress energy tensor. It is the sum over the beta functions of all the operators that you have in the theory for marginal couplings, right? Good. So like this, so if I would like to express this guy, so this guy will be a sum over beta functions, beta I, beta j, or I, oj at some point. This is important. Okay, good. So let's keep that in mind, that the g function is like this. And also look at the h function, by the way. The h function has one component of it, which is this guy, tzz bar. This is also t mu nu, right? So if t mu nu is, you are a fixed point and it vanishes, this is also going to vanish. This is important. Good. So then, by the way, these functions are defined with a scale. So they're a function of z star. So here, they're a function of z star, which is the absolute value of z, the magnitude of z, and u. Okay, that's not an important point. Now, here is the intuition of Simological. This particular heavenly given C function is a combination of these three functions that we just talked about, f, g, and h. Oh,
Yes.
Well, don't please ask me why, okay? F minus half of h minus 3 over 16g, okay? Don't, please, okay? It is what he wrote in the paper and what turned out to be true.
Yes.
So we constructed that function as basically this linear combination of the f, g, and h. And we want to show that this function monotonically decreases along the RG flow from the UV to the IR, and it's equal to the central charge of the conformal fixed point. Good. Now, the conservation equation, this property here, del C by del log Z, follows from the conservation equation that we just explained here. This is simple algebra. But the most important equation of all is this guy. What is this telling us? What is this telling us? Remember that beta I, this piece, Basil, this piece, is the generator of local scale transformation.
Yeah, I guess we should be a little bit slow here and say that to go from 1.27 to 1.28, we're using an RG independence argument. Like if we were to take total derivative of C with respect to the scale given by log Z, then we would get 0. But that total derivative is really partial derivative by chain rule, plus what you get by taking the derivative of the coupling dependence of C with respect to the scale, which gives us d over dg times dg d log z, which is beta
d log z. Absolutely.
And that's why the sign flips, because there's a plus, and basically that total derivative equals 0. So then you take this as an implication. That's so 1.27 to 1.28 is coming from an independent statement. Sort of.
Did you work that out in your previous podcast?
No, I mean I breezed through this because I was mostly going through the Osborne derivation.
The local derivation. Good. So yes, but what you mentioned is exactly right. This is why there's a change in sign.
Yes,
going
exactly.
From 127 to 128, and it has to do with exactly the total derivative being partial derivative, and yeah. So if maybe I should slowly here, but
it's fine.
Let's yeah, maybe I'll yeah, okay, fine. Maybe next time I'll share. I'll use my my new pen, which hasn't arrived. This is which works intermittently, but I'll definitely maybe come back to this at some point. Yes, and
right.
Okay, so if I start from this 127 and look at the left-hand side, and sorry, 128, you see that beta I del by del gi is the generator of
the local scale
transformations. Local scale transformations, absolutely. And here we denote the I think the couplings. Did I ever? Yeah, that was my bad. Let's go to the conventions in this paper because it was defined. It was defined. Yeah, that's my.
So it's GI are the couplings, and then
GI are the couplings, right? And then
DGDT, if you want to call it, is beta.
Is beta. Good.
DGDT.
Yes, exactly. Good.
Which
so
is,
this is the convention here, right? DGDT.
Yeah. I think so. Yeah.
Good. So let me go back again to the
Sure. Yeah, to the homological result.
That.
Yeah.
Yes. Good. So let's see. Beta I. Here
to be DGD log Z, because I think log Z is what is being used as the
log Z, or actually he's using that's the UV cutoff because usually okay. Yeah, fine. I was fine. Okay. So usually in different contexts, you find that Zamolodchikov uses as a UV cutoff, which is basically a better one, A
Yes.
as a UV cutoff, and you find that in this sense, beta I is like A del G by del A, or it could be something like or dG by dA.
Right,
Right?
right,
And then let me this, or you can define it as, of course, dg by d log a.
right.
So here he's using log z, but yeah. So there's this one important ingredient which I neglected to mention is that there's an intrinsic UV cutoff of the theory, which defines, maybe as I mentioned before, as we flow, right? I mean, in any RG. Good. And
Yes,
so if
yes.
you look back at equation 128 again, you see that the left-hand side, let's read it carefully, is the operator of local scale transformations acting on this constructed C function,
Mm-hmm.
right? Equals to 3 over 2. Beautiful.
Yes.
Let's take a look at it and see what's going on. So I have an equation that tells me that I have an operator, beta I, del by del gi, which is think of it as an operator that generates local scale transformations in the RG space, acting on C. So it generates local scale transformations on C, which is this C function that has F, G, and H. There's an implicit dependence here on the UV cutoff. So HC depends on this UV scale, right? A,
Yes,
or
yes.
which will be epsilon in the off-shelf formalism. And it's equal to 3 over 2g. But
Yes.
what is g? Let us see.
Right.
G
G
was
is
very
the trace
special.
2 pointer. Yeah.
Exactly. G was the special function because it's a 2-point function of the trace of the stress energy tensor, right? It's the trace.
Yes.
Good. So what we have here is something which is proportional to the stress energy tensor, to the 2-point function of T mu nu as a function of X, right? And then
Mm-hmm.
T mu nu as a function of 0 and X, right? It's
Yes.
proportional, and we'll see in a second what the proportionality factor is. It's going to be important. But look, so if your fixed point, T mu nu is 0 on the right-hand side, but beta I is also on the right-hand side, or the left-hand side will vanish because T mu contains beta I. And look at the
Yes.
definition that we said is going to become important. We said that we can always write T mu nu, which is D D D bar, as a sum over all the beta functions that you have in the theory times the operators corresponding to the marginal couplings.
Yes.
Okay.
Yes.
So good. So that's what we have right here. That's important to keep in mind. So what we have on the right-hand side of 128, this innocent looking G, is some beta functions and some 2-point functions of operators that will
Yes.
be written here in a second. This is very important. It's at the core of what's going on here. Now,
Yes.
let
Yes.
us write the trace anomaly equation, the 123, which is this one, and define another function called gij. This function of 2-point function of operators representing two marginal couplings. Right? We're talking marginal couplings. Marginal couplings means basically you're deforming your away from the conformal field theory by massless deformation. So this is a massless, right? That's what by marginal. And in string theory, we'll be talking about exactly marginal versus nearly
Right.
marginal deformation. This is important, so to keep in mind.
Yes.
I'll come
Yes.
back to this because there's different notions of exactly marginal and nearly marginal, and it's very important here, especially in string theory when we talk about marginal deformations. Okay, let's come back to let's not so good. Go on tangents, and so TZZ bar is beta things, and so now he constructed another function called gij from the 2-point function of these OI OJ. Now I can
Yes.
simply write 128 as this 130. Why is that?
Yes.
Well, that's because if I write T mu nu, remember T mu nu is basically, I can write this as TZ bar, right? So I can write this guy instead of T mu nu as TZ bar,
Yes.
right? Because we said this in the complex coordinates, T mu nu becomes TZ bar. But then, as you can see, if I want to take the 2-point function of TZ bar, this will basically be something like related to beta I,
Yes.
beta
Beta
J,
O. Yes.
and then the 2-point function of OI of X and O J.
J of 0. Oh, yeah.
Zero.
Yeah.
Right. And right, so that is sitting in the right-hand side of 128. Okay, so GIJ in 129 is just this part of 128. Right? So it doesn't have the beta I, beta J,
Yes.
but it has the 2-point function of the two marginal operators. Good.
Right, right.
So now I can write 128 using 129 as it is in 130 and say I have 3 over 2 GIJ, beta I, beta J. And of course, there is an inequality here. Without this inequality, and this is what's known as the homological C theorem. Why is it the C theorem? Well, now let's just pause and think. We said before that we have two spaces, the physical space-time with a physical space-time metric. We have the RG space, which is the space of infinite couplings, the space of theories, because each combination of values, so if it's a configuration space. So each particular set of couplings, each values of a particular set of couplings in my theory, which are taken to be infinite, defines a theory. So whenever I
Yes.
flow, at each point in the configuration space along the RG flow, I have a different values for the couplings, and this defines a theory in the RG
Yes.
space. Now you can imagine you put a metric on that theory. Whenever we have a space, an abstract space, doesn't have to be space-time, it's legitimate to speak of a distance between theories on the space. How can you quantify a distance between objects in that space? Objects in this space are definitely theories, right? How far, right, is one theory from another? How far is one theory from another? So it's really like this. It's really like I have a line, and you start from a UV, and I end from an IR, and you have to hit a theory, it is a theory, it's continuum, right? So it is a theory, it is a theory. And it's legitimate to ask, okay, is there a notion that I can quantify the distance between any 2 points in this theory? This is very rough, but it really is. I have but really delivers the point. In each point, there is this line defines a theory, and I want to quantify distance between the theory, just like we quantify distance between physical space-time, physical space. Good. And for that, we need a notion of a metric, as you know. And this metric happens to be this innocent-looking 129 2-point function between two marginal operators. And we know that if you want to define a distance, a notion of a distance, by definition, is positive. You cannot have a negative distance. So, will this translates in 129 to a notion of a positive definite, to be a distance. A distance cannot be negative.
Right.
Good. And so it happens that the 129 is a positive definite function. And so if it's a positive definite function, it can function as a metric on the space of theories, the space of couplings, right? In RG space. And because we're flowing from the UV to IR, and because GIJ is positive definite, and because as you go from UV to the IR, what happens as you go from UV to IR? You're basically integrating over degrees of freedom. You're basically saying, I have a UV, there are lots of microscopic degrees of freedom. And as I flow to the IR, you're summing over them, you're averaging them, you're just removing them from the theory. So it makes sense that the number of degrees of freedom in your IR as you flow to the IR is basically fewer than those in the IV. That's the statement that the CUV is less than CIR. And that's why we say here that this function is monotonically decreasing under our renormalization group flow from the UV to the IR. Here's another
Yes.
point. That's important because if it fails, so this is going to be important in what comes in string theory, because if this function that you construct does not have this positive definite thing, the theory fails. The
Yeah.
statement of the C theorem itself fails.
Yes.
And this is on the sphere, the worldsheet sphere. When we go to the context of string theory, it will fail.
Right. Yes.
And we will try to see way out of it, but it will fail. So it's not always guaranteed that this function, that this positive definite metric or function is always positive, it always exists, and therefore there's always this D theorem.
Right. Right. No, that's a very good
Yeah,
point.
go ahead.
I did only very briefly touch on that, but I think it'll be very interesting to dive into what the failure modes of this are. And I guess that is one of the motivations of starting here and starting slow here, is that we'll see that each of these things you can't take for granted once we generalize to the case at hand in worldsheet string theory, where we have an nonlinear sigma model, and we're going to have to deal with the fact that, well, C would just be zero, right? This is sort of like the whole point of the construction. You read Polchinski and you're like, of course, I mean, you want C to be zero, so what's going on? What are we talking about?
Apparently, if you define it, if for those who know that string theory is defined by conformal field theory and the worldsheet that has a central charge zero, and suppose you want to start from a particular string theory in the UV and then defined by S equals 0 CFT, and you flow by some quantity you construct, which is similar to this, but it doesn't have to be exactly this. And you flow in the IR to another conformal field theory, to another string theory defined by another C equals 0 string theory. Well,
what exactly have we done?
130 is not satisfied because it's just zero. You start from a quantity is defined as zero because it's equals 0 central charge, and then you flow to another point which is Z equals 0 central charge. So even the monotonicity is not there. So one has to be a lot careful. And when you add string theory to the mix, it's not as straightforward as it is in two-dimensional case. Plus, this is, again, let me remind the readers that this is constructed in flat space. So the proof that we are presenting now is in flat space-time, right?
Right.
And once we go to some curved, like for example, curved worldsheets, the sphere, things are more subtle.
Right. Yeah. Let's dive into it.
And so let me at this point, it's important to remind the readers of what is to come when you add these more extra ingredients to the C theorem.
Yes.
Let's continue here. At a fixed point, we see that the beta function G star is the value of the coupling at this point. So at each point of this, there is a particular value of G. So here there's a set of couplings here. So here's GI. It flows. At each point of this is there's a GI. At the IR, there's a G star I. G star. Maybe I'll try G star I to denote that. G star I. This is the fact that the couplings are defined at some fixed point. So this is what we call the fixed point. And now fixed point means that, what does a fixed point mean? A fixed point means that if I go back to 128, I apply a local scale transformation operator on the left-hand side on the C function, and nothing happens. Nothing happens, doesn't change, it doesn't scale, so this is zero. So 129, 128 is zero. That's what it means. Your theory is not responding to the change in scale anymore, right? That's what it means to hit a fixed point. So let's look at 128, this innocent-looking 128 or 130, all right? On the left-hand side, we have the beta functions. The beta functions are, by definitions, the derivative of your couplings with the UV scale, the RG scale. Well, If the theory is not responding to changes in the scale, that means the beta functions do not vanish. The beta functions vanish because it's not, the couplings are not responding to changes in scale on the left-hand side. So what is there is going to, C is not going to happen. C is not going to vanish. C is a generic function. So beta functions are going to vanish, which basically means that this guy is zero. There's no change. The couplings are not changing in scale. Good. And on the right-hand side, what do we have on the right-hand side? What we have on the right-hand side is the 2-point functions of
beta O.
the stress images are beta O. So good. So that means I have TZZ bar is zero, right? Well, the trace of the stress energy tensor is zero, which is what we started with. We said that whenever I have a symmetry, a local Weyl symmetry, T mu nu is strictly zero. And T mu nu is strictly zero here, as we see in 129 and 128, means that the beta functions are zero. So the beta functions vanish, the TZ bar, DZZ bar vanish, the trace vanishes, and this is the statement of being at a fixed point. Okay, on shell in string theory, this means you're on shell. That's basically anywhere along the RG trajectory from the UV to the IR in string theory is called off shell. Only at the fixed points you are on shell, and we're going to counter that in precisely what it means. But this is just to tell you that if you are at a fixed point in the string theory context, that means you're on shell, right? And this is basically the more or less. There's a lot of details that one can get into and work out here, which we can do next time, by the way. In the 2D in this homological C theory. But yeah. This is it. Do you want to us to get into the non-linear, or maybe we'll keep this to next time? It's up to you. We can.
Yeah, well, we can sort of like just preface what the differences are. So I mean, the local version of this was reviewed, so that's good. And now we have a detailed understanding of the homological version. But I suppose what we should preface is the context where, you know, as you mentioned, there are these subtleties and exactly where they come from. So, yeah, I guess you can proceed with the just laying out the problem.
So I will start here with chapter 7 of David Tong's notes, which are beautiful and they're online.
Yes.
This is chapter 7 of David Tong's notes. They're not mine.
Shout out to David.
So let me shout out to David. So let me here say David Tong's notes on string theory. Lecture notes.
Yes.
Okay. They have in chapter 7, he discusses low energy effective actions and some quick introduction to nonlinear signal models. So I'll spend some time here. Although you can say, oh, this is chapter 7 in string theory notes. There's 6 chapters before, but no. Let's just take a moment and say, okay, suppose I give you now for the readers. I'm going to assume you have some string theory basics. So I'm going to assume you know what a worldsheet means, what a map to target spacetime means. You basically have under your belt either David Tong's notes or Polchinski version 1 or you know whatever. So you know some string theory, okay? And so you know what a worldsheet action is, and you know what the Polyakov action is. We know that in the standard Polyakov action that we learn in Polchinski in string theory, this guy right here is eta mu nu.
Mm-hmm.
And eta mu nu means flat metric. So you're always learning to quantize string theory in flat target spaces. This is the two-dimensional worldsheet action, and this is the worldsheet metric. This is the standard kinetic term, and this is the, instead of writing d sigma, d tau, we're just in convention where it's d2 sigma, and that's why we get a factor of 1/4. Okay, good. So now suppose we would like to quantize this. This is a sigma model. This is not a priori string theory, in the sense that it defines a zero Weyl anomaly, right? And we define string theory by a zero central charge, and to start with, when you work the Virasoro generators, you get the d equals 26 from the condition of Weyl symmetry, Weyl invariance, the vanishing of a Weyl anomaly. And that's why you get the mass shell condition. So string theory somehow, for some philosophical reason, loves CFTs.
Yes.
Okay, but there's nothing intrinsic in that. This will get into the philosophy of what's going on here, because there are two different viewpoints. This has always annoyed me. We start with string theory, CFT with a zero central, and then we move on. Well, we're going to have to break this paradigm a little bit as we move on.
Yes.
And so if I give you a metric in target space, was like this. This is a metric, G mu nu, which maps you from, depends on X. So this is G mu nu of X. X itself is a function of sigma 1 and sigma 2.
Yes, yes.
And this G mu nu is some metric, could be whatever.
Yes.
It's a nonlinear map from your world sheet to your target space. A map that will take you from ZZ bar to X, and from G mu nu itself is a nonlinear map. So that's why the nonlinear sort of sigma model, because the map from the world sheet to target space is nonlinear in nature. And there are linear sigma models that exist out there. And therefore, but look, one more thing. This is now an interacting two-dimensional field theory. It's no longer free.
Yes.
So now you see why this is relevant. What we just discussed is relevant, because right now I have a two-dimensional field theory, two bosons. Well, except here that X's are maps into target spaces, which introduce further constraints. But this is basically two bosons. It's a boson, free boson, not a free. But now, before that it was a free. But now they're interacting. This is a coupling. So this is an interacting two-dimensional field theory on the sphere or projected onto the plane. So right now, we assume that we have some stereographic projection of the sphere onto the plane. And we have a theory that is no longer free, but it's rather coupled. And the coupling is this metric G mu nu. So I have an interacting theory. Oh my God, so good. So I have a 2D theory, and it's interacting. And the G mu nu is the coupling. It's no longer the lambda, the innocent looking lambda or G and the homological. It's a beast. It's a nonlinear map to some unknown target, some target space.
Yes.
And the target space itself has a metric. The metric in the target space is built by something which already is not known. So you can ask me, what is the metric on the target space? Well, the metric on the target space is going to be built now by this coupling, which is itself is the metric, right? This is one of the very beautiful points of how string theory builds your space-time rather than space-time itself being taken as granted, and we'll see now.
Yes. No, this is crucial. Yeah.
This is crucial. So G mu nu, guys, here basically plays the role in this two-dimensional homological theorem of your coupling G. And so what we have here, so it's legitimate to ask, is there a flow? Is there a non-vanishing beta function? Yes, there is, because it's an interacting two-dimensional field theory. There's a non-vanishing beta function. Beta functions are generator of scaled transformations, and it flows to what? In this context. We'll keep that question in mind until next time, but it's a legitimate question. And now you can see why it's more complicated, because we have a CFT, a zero central charge, and our innocent looking and position independent couplings G are now beasts and now nonlinear maps into target spaces.
Yes, yes.
And
Yeah.
that is the first generalization, right? G mu nu is and why? So G. So first of all, so G was constant. Here is this is not a constant, and so in a sense, like this is local RG.
Right.
Because my coupling on the in the 2D interacting field theory depends on X in target space. X are coordinates in the target space. But on the field theory sense, they are fields in target space, we have the couplings here, and they depend on X, and X's depend on Z.
Yes.
So
yes.
they're local RG in that sense versus what we just explained, which is just RG, which is not local RG. So that's another complication. So we see the differences here between and the more complications and the more layers that are going to come into when we add string theory and nonlinear sigma models.
Right, right. Oh, that's great. Yeah. And
do you want me to move on or
yeah, we could totally move a little bit further before.
Let's at least move on continue for like 5-10 minutes and then
and then wrap up.
And then this is important. So let us now compute the Polyakov path integral for this guy. So suppose I want to compute the Polyakov path integral for 7.1, right? So I want to compute the path integral Z, right? And quantize 7.1. Beautiful. This is one of the most beautiful pieces of string theory ever. And
yes.
And actually deep. And I think there is no satisfactory answer. And I'll tell you why. And okay, so suppose I want to expand the metric around flat space. So I do not want any crazy metric. Let's take it slowly. I want something which is not flat, but it's a perturbation away from flat space metric, flat space time metric. Okay, let's reason. We'll start slow. And I introduce H mu nu. I think this is Euclidean.
Yes, yes.
Delta.
It's delta, yeah.
Good. So now I can compute standard partition function path integral dx dg, of course, e to the minus Polyakov minus v. What is e to the minus Polyakov minus v? Well, this guy, because we just said that this g mu nu is delta mu nu plus h mu nu. Then when I take e to the minus this guy, this part of it is Polyakov.
Yes.
So this is where this comes from. This part of it is Polyakov, this here. This comes from the fact that, and the v right now is coming from the fact that this is h mu nu. So v looks like this. Let's start here and say, okay, v looks like this. This is what we mean by v, right? Because so the first part of my S, I'm taking this, is going to be S to the minus S Polyakov because it has the, and then e to the minus v, so minus v, which comes from
H times the dx term.
Exactly. This part, just this.
Right.
Okay, cool. Now I expand. I have an exponential, just like we do in interacting quantum field theories. I expand my exponential of the v in v. So I expand in v because v is the perturbation. Beautiful. So far so good. Okay, so I expand. And I have this expand in v. So each exponent is v squared is okay. So it's a 2-point function. So v squared here is a 2-point function because this is path integral, of course. So this is a 2-point function of this vertex operator. 3-point functions, 4-point functions. So of course This now is the generating function of my correlation functions. Because
Right.
functional derivatives of this object will give me my correlation functions.
Yeah,
Good.
of vertex operators specifically.
Of vertex operators, precisely. Vertex operators in this case. We haven't. Now, the surprise is I haven't told you anything. So suppose I start teaching you string theory from chapter 7 of Tom's notes. Forget about
Yeah.
everything else you've learned from Polchinski. Forget about you start from a conformal field theory of zero central charge. Forget about the genus expansion. Forget about anything, right? Suppose this is your first encounter with string theory. I give you maybe a couple of hours before this, and I tell you that there's a CFT and there's something called zero central charge and maybe a little bit about ghosts and stuff like that. Just a couple of hours. And then I'm going to write and start with chapter 7. I tell you, okay, here is my signal model. And I tell you, here is the vertex operators. Well, I lied a bit because someone will have to probably know what this vertex operator in 7.2 is, that
Sure.
from the quantization of the closed string, and that this is how you get the gravitons. But so if you've done,
I mean, or I mean, you could take it a different way. You could just say that okay, you have the free boson CFD, you have so many free bosons, and now we want to do two things at once: put it on a curved background, or put it on a dynamical background, and consider the correlation functions of non-trivial conformal primary operators. Well, those aren't the elementary field operators. They have to be either currents or they have to be exponential type operators, which for lack of a better term, we call vertex operators. So with the two things that you can actually have, the right kind of scaling behavior, you basically immediately run into expression like 7.2 plus the preceding expression, because that's going to be what you can actually use to start building up your table of non-trivial conformal primary operators and so on.
precisely, exactly. Thank you for this. Exactly. I could have started with that as well. I mean, take this as my definition
Right.
of creating a graph of a vertex operator in the theory, and instead of starting with quantization of the string and some gauge, and then realizing that this is the vertex operator of the graviton, that and that's why string theory contains gravity. But look, so if you know 7.2 from before, you know that when you quantize the string, closed string, you and then you have the Hilbert, you construct the Hilbert space, you see that it contains the graviton as one of the massless modes. Oh, so it has the graviton, and this is the vertex operator. Come along here. Of course, if you add the, I'm assuming we identified H mu nu with the
Yes.
polarization, and then hit a to the IPX because it's the actual Fourier mode. I mean, this is how we define a vertex operator. Then suddenly 7.2 is precisely the vertex operator that we insert on the world sheet to create a graviton, which is a quantum of the space-time in target space.
Yes.
So where did this come from? It comes from G mu nu. So what does this mean? If I want string theory, so string theory builds my space-time for me. It's really crazy if you think about it, because we say a gas of these vertex operators, because remember, there's a lot more, these squared, these. So a
Yeah.
gas of these gravitons, what I mean by a gas, just to be clear, this is my gas. A gas is these guys. This is a gas
Yes.
of gravitons. Each graviton is represented by an insertion on the world sheet of this vertex operator. So an insertion of a vertex operator on the world sheet represents creating a graviton that comes from minus infinity in targets. It propagates from minus infinity and in target space. That's what we mean by a gas of gravitons. A gas of these gravitons, a gas of this 1 s 1 plus v squared, builds for me my G mu nu. Remember, my G mu nu is this, right?
Yes.
This is my G
Yes.
mu nu. So H mu nu is my polarization tensor, which contains
Yes.
all the information that there is about my metric. So your metric G mu nu is built, so here's the statement. The space-time metric in string theory of your target space is built from inserting a gas of gravitons on the world sheet. So of a flat space-time, flat. Remember, we deformed away from flat. So give me a flat space-time, flat. Insert a gas of these vertex operators, you get curved space-time. Curved.
Yes.
Maybe it needs a little bit to think about, to appreciate the depth of what's going on. So you start from a flat space-time, and then on the world sheet, you insert a gas of these vertex operators, and suddenly your flat space-time is curved. And
Yeah, I think that the real insight comes exactly in the 7.1, where you're kind of bringing to life, well, I mean, from the basic calculation that'll follow, we sort of bring to life version of the well, of the local equivalence principle. So, I mean, if you proceed, you'll see that what one finds is in the background field expansion of X, right here, which is what's going on even at the level of the metric. But if you were just to think about this background field expansion, and we wanted to maintain the covariance, right? So beyond just what we do to G, but also what we do
yes,
to X.
yes.
And if you wanted to maintain the covariance, there's only one way to really do it, right? That way would be,
Yeah,
if you're being cognizant of the equivalence principle, then, well, what is that going to be? It's going to be something like a normal coordinate expansion, some
yes,
geodesic normal coordinate expansion. And that will immediately tell you that, first of all, 7.1 is a sort of innocuous repackaging of an otherwise very complicated action involving an infinite number of couplings, because
yes,
you just keep, everything just keeps growing in this derivative expansion. So if you really wanted to make sense of this gas, right, beyond just fluctuations around flat space,
yes,
then you have to accept the fact that there's going to be some infinite number of these contributions arising. But that those contributions are all, they know about completely covariant objects from the target space perspective. That are the curvatures, the squares of the curvatures, and so forth.
yes,
So if
absolutely.
we just proceed, we'll see that actually we're going to get already as leading quantum correction the pieces that will give us the it's the basic vacuum Einstein equations in the target space, which is sort of the very important and historic result that the RG flow is captured by the Ricci flow
But the
for these
Ricci
models
flow and
and beyond.
the mysterious equations, the beta functions,
Yes.
of this uh, innocent looking 7.1, which is not just there's one coupling, as this is an infinite number of couplings, by the way, guys.
Yes. Yes.
One coupling here, because G mu nu will be expanded. There's going to be an expansion in the derivatives of X, and this is what we call the sigma model expansion, by the way. Now,
Yes.
the alpha prime expansion of the sigma model expansion. So this 7.1 will turn out to be an infinite number of couplings. So this is a very highly interacting field theory in 7.1, and the couplings will have beta functions, and the beta
Yeah.
functions
Let's
are
see if we can
going to
get to like at
be.
least one loop here, because I think that that's already a
Yeah,
fairly
yeah,
compact.
I think we can do one loop, but
Yeah.
um yeah, I think we can do one loop. So suppose that I and by the way, I mean, yeah, this yeah, let's go do that here. Suppose I usually before I do any actual computations, you want to expand your string coordinates in this way. Uh,
Exactly. Exactly.
and
So
this
this is the
expansion works
background field
better.
expansion. Yes.
This is the background field expansion. You say, I have what we call the zero mode. That's called the zero mode of the string, because notice it's not a function of the world sheet coordinates anymore. It doesn't vary with it. And by the way, this is what ultimately appears in your effective action. What we're going to derive is some effective action in target space. I mean, it's not it's not very clear in this approach. It just connects the beta functions as equation of motion. But as in Centlin's formalism, there is a clear way to derive the Einstein-Hilbert action from the sigma model, right? You want to derive
Right.
the baseline Einstein-Hilbert action. It's beautiful. No one would have thought that if you start from a two-dimensional interacting field theory on a world sheet, I can end up with the Einstein-Hilbert term in a d-dimensional target space. Who would have told me this?
Yes.
Why? Why, right? That's why string theory knows about gravity. That's why it's a theory of gravity, right? And that's why we're doing what we're doing because of this. So suppose I expand my coordinates in a constant mode, x bar mu, and some fluctuating modes. Now, the idea is when I compute the path integral, I do my derivative. My integrals are, instead of being over dx anymore, this is not there anymore. It's going to go to the integral over y.
Yes.
Y of sigma. And now there's you're going in your path integral, there's going to be an expansion in derivatives of y. And this expansion in derivative of y is going to determine the loop expansion, alpha prime expansion, forgetting about x bar mu. So this is why it's going to integrate over the fluctuations around x bar mu right here. And then depending on where you stop, you're going to get an effective action to a particular order in alpha prime.
Yes, yes.
And so if I would like to rewrite, for dimensional reasons, of course, we know the factor of alpha prime is there because, of course, the dimension of x is -1, it's length after all. Y is 0, right? And that's why it has square root of alpha prime right here.
And that's also why there's an alpha prime expansion, is because that's how the alpha primes come in, the extra alpha primes. Despite there just being 1 over alpha prime in the action, you get more in the alpha prime expansion because it's an expansion secretly in the fluctuation. So it's telling you how far. Yeah.
Precisely, exactly how far you move away from your CFD. So if you expand this guy now using this coordinate expansion, it will look like this.
Yes.
The first one is nothing but g mu nu as a function of the zero mode or the constant mode. And then the second term is g mu nu comma omega or w, which is basically one derivative of the metric
times y
times mu one. Yeah, and then notice that what's going on. This is alpha. This is square root of alpha prime. Now this is becoming alpha prime. See alpha prime here, right? And then you have two derivatives of g, and then y omega y rho. You're just expanding in this.
Exactly.
So del x is going to be del y, and then the derivatives here is going to act on the g, and they're going to be left with the w's right here. And here's setting all that. So now each of these coefficients in the Taylor expansion is a coupling constant. That's why this g mu nu is an infinite number of coupling constants. Although it looks like a one coupling constant on the world G theory, it's an infinite number of them nicely packaged into the g mu nu. Good. But notice that for this to work, you have two length scales. String theory has this length scale that makes it distinct from any quantum theory of gravity, which is the alpha prime, the fundamental length scale, right? Alpha.
Yes. Yes.
Alpha prime. Right. This is different. This is something that distinguishes string theory. And by the way, this is the reason why, as we're going to explain, Susskind Ugolum on the sphere makes sense.
Right.
Because otherwise there was no even hope, there's no even sense to make sense of this. Again, I'm digressing. But this guy right here, J. Newton, is in string theory proportional to GS squared alpha prime.
Mm-hmm.
And usually, when we say A over 4G, what comes to mind is A over 4 Planck length squared.
Mm-hmm.
And it's if you, again, you tell people, I would like a microscopic derivation of the Bekenstein-Hawking entropy, you're nuts. The reason you're nuts is because you would like, sorry about that, but people will call me nuts, and I've been called that because it is, you require a non-perturbative theory of gravity, because basically in the denominator, there sits the Planck constant, Planck length.
Yeah, you need to get that out. It's the only, how will you transmute that if you didn't know, right? If you couldn't actually control the
Precisely.
the short
But
distance
what
physics.
the point, the idea of Susskind oblong, which we'll come to, is that in string theory, when the low energy, even at low energies, you have
Yes.
in the denominator G Newton, and G Newton has an alpha prime down there, and
Yes.
there's a GS squared, and GS squared means it's a sphere.
Right.
So if you, that's the whole idea of Susskind oblong, right? Without this observation, things will not make sense. That if I want to make sense of where G Newton is, derive G Newton, induce G Newton, take it not as granted, take it as something that comes from something more fundamental, being the world sheet. I have GS squared down there. This is what's called the string coupling constant. And the string coupling
Yes,
constant
and
means, it means a sphere.
because
So
it's
then I
GS
need to make sense of
squared,
the
it's
sphere.
GS to the power 2 minus 2G, where G is 0.
Yes. Yes.
Yes.
So this is very rough. Exactly. It's d minus 2. So it's going to be this. So GS squared means that if I want to make sense of G Newton and Bekenstein-Hawking entropy, I need to make sense of the sphere contribution to the entropy.
Absolutely. Yeah.
And this means that suddenly in string theory, I have a doorway to make sense of A over 4G rather than having to wait indefinitely, maybe indefinitely, to define a non-perturbative theory of quantum gravity like what you have initially thought.
Yes, yes, absolutely.
Okay, this is just to make sense of the importance of alpha prime. It's a digression, but it's important because alpha prime and this intrinsic fundamental string scale is the whole reason why you can make sense of this A over 4G in string theory to start with. So now going back to our sigma model expansion right here, for this expansion to work, it's a perturbative expansion. For a perturbative expansion to work, you need a small length scale and a large length scale. Things have to work like that, right? And so we have here a length scale, which is square root of alpha prime, but we have the fundamental, we have the target space length scale of your target space theory, which is RC. For this expansion to work, for every derivative of this, remember this is del G, mu, del omega. This is the derivative. This is a derivative.
Yes.
For this derivative to work, it's basically schematically looks like this: 1 over
Yep.
RC. Okay, so for each derivative here, you have alpha prime, for example, this is alpha prime. So let's look, this term is held alpha prime over RC. Right? Alpha prime over RC. So
No,
RC,
yeah.
huh? Yeah.
Oh,
So,
yeah,
so
RC
this term
squared
right here.
probably. Yeah, you
What's that?
probably want RC squared there. Because you
RC
want square
squared,
root
sorry.
alpha. Yeah, yeah, yeah.
As for C squared. So for this to work, for this term to work, alpha prime must be actually much larger. So RC squared must be much, much smaller than an alpha prime. For this expansion to work, when there are regions of space-time, when the radius of curvature becomes of this order, then the world sheet theory is what we call string decoupled, and we run into other slope problems, and this is important. This thing.
Yeah, I think that there's a purely geometrical way to think about this too, from the perspective of the target space. And I think that, I mean, I'm only saying this now. I hadn't had this thought before. But I think that the way we think about the background field expansion in string theory is actually wrong. And people, how they would normally think about it is they'd say, oh, well, we're in this flat world, and then we're from somewhere, there are these gravitons coming, and then, well, look, it's changing somehow. But this is a process one would never observe. Because, I mean, it's absurd. Where would gravitons come from somewhere? No, it's really that you're close. Like, how would we think about a normal coordinate expansion in general relativity? If this is a whirl line, right? We would be very close, right? We would be basically sitting on the whirl line, and then everything looks flat to us because that's the equivalence principle, is what it does. Now, when we start to move away from it, right? As in, if we were actually, like basically how you would witness curvature, right? Through geodesic deviation. If we're actually going to start to move away from it, then we would build normal coordinates where the leading deviation, which we will come to very soon, the one loop correction, the leading deviation, right, which is where you start to feel the effect of RC, will come from the curvature, right? Then you start to feel tidal forces, right? And as you keep moving, this is where, you basically start to like witness what the rest of the space is actually doing once you start to like get a little bit away, right? So I think that the right way to think about this, I mean, this is just an extended object, but our intuition should probably track with the same intuition that we would use for geodesics in a whirl line, right? If you wanted to really think about this expansion carefully, because that's literally what this expansion is. And I mean, we'll look at the derivation here, and then we'll briefly switch to Fradkin-Zeitlin, where it was done in the covariant framework from the very beginning. Right. And then it becomes clear that the right way to interpret it is that you're maybe thinking that you're in an isolated region. And if you're in an isolated region, then there's some sense in which you could witness scattering events, right? Because that's what any asymptotically flat region means, practically. It's an isolated region, right? You don't see the effects of maybe there being a cosmological constant, maybe there's something else, maybe there's, like a black hole or whatever. Maybe you find so you find yourself in this region, you see some scattering events, but in fact, just move away a little bit. If you could zoom out a little bit, you suddenly realize that no, this is just a small piece of this bigger space that has all kinds of other things going on, which is described by whatever, the more complicated string dynamics. And from that perspective, the story makes much more sense. This prescription, right? When you're at, basically, because you see this alpha prime expansion, or the weak coupling expansion, is literally tracking with the expansion in the background field, which is literally the normal coordinate expansion, right? It's like the geodesic normal coordinate expansion. So you're measuring this in terms of essentially geodesic deviation, right? And so there's exactly the sense in which one should properly interpret what you mean by talking about string backgrounds, right? If you really thought about it, because the string background, when you're sitting, just C equals 0 flats, like, where you can do the Polchinski calculation, is when you're in an isolated region where you can think about the S matrix as being defined truly in terms of some asymptotic region, right? And in reality, it never is, right? As in, when we go to the LHC, of course, there's never a sense in which we actually need to go build a detector as big as the sky even. No, it's a detector which is large compared to the characteristic energy, the wavelength, so 1 over the characteristic wavelength of whatever scattering inside, right? The detector might as well be at asymptotic infinity given the scale hierarchy, right? But for the perspective of whatever is scattering inside the LHC, the walls of the LHC where the detectors sit is like asymptotic infinity, but it's an isolated region, right? It's sitting inside an isolated region, and that's why you can make sense of it. But of course, clearly, as you go out, even if you just look at the scale of the Earth, there's a gravitational field, there's some curvature, there's all kinds of other things going on. And I think that this, I'm only bringing this up because there's a lot of talk about, or there's some people who have a lot of talk about issues such as background dependence or independence in string theory. And there, they always compare it to, say, general relativity, where you would say, oh, no, look, in general relativity, we have this notion of background independence, which means that we have this, which is basically talking about off-shell phenomenon, right? In what sense is general relativity background independent also? It's only in an off-shell sense. Because you see, once I commit to a solution of the field equations, I'm given a set of rulers and rods and clocks, right? That this is just, I'm committed presumably to some gauge, some coordinates, whatever. Yes. But it's because I know, oh, I fixed the gauge, I integrated the equations in that gauge, that I'm getting whatever I'm getting here, right? But here we'll see that basically the net effect is that any meaningful physical object, like a force, right,
Yes,
will immediately be sensitive to covariant things such as curvature. And that's why I thought we would get to
absolutely.
this one loop result, which kind of solidifies this notion. And this is fully covariant. I mean, even though this expansion is not covariant, you'll see that the result is going to be covariant.
Yes, yes, it's a result is going to be covariant precisely, and I love this. I love this digression about what it means to have a string theory background. And one of the things that we learn is exactly hits on that point, is that you only can compute in string theory, again, which means on shell, S matrix. You cannot compute correlation functions. Why? It's exactly for the reason you just said, right? The standard lore is that there's no sense you can compute correlation functions in the sense of quantum field theory correlation functions. And there's something called an LSZ theorem that will
Yes.
truncate some external legs and bring them on shell, and you have them, and then you can compute S matrix. It can only make sense of states, all right, well, we call them vertex operators, corresponding to states that are asymptotically traveling from minus infinity and going to plus infinity. There's no reason, there's no way we make sense of, because once you see correlation functions, you're truncating the legs at a certain point, which basically means
Yes.
you're sitting at a different space, in a different in a different neighborhood rather than just asymptotic infinity in this box, in this confined region. You're sitting in
Yes.
different, so you're asymptoting the external legs of the propagator, the coming in propagator, but you're not propagating in from infinity, which is
Yes.
the standard assumption that you use to do a conformal transformations from something which comes from minus infinity to conformal transformations and convert them to standard vertex operator insertions as defects in the world sheet. I mean, that's a standard thing. But if you don't have these conformal transformations, then how do you make sense of basically something coming from minus infinity as a vertex operator insertions in the world sheet to start with? Right? You have this conformal map that takes you
Right.
from a state that is propagating from minus infinity. But but that comes back to the point. That is what they call a string background and a conformal field here, because it's conformal map. Once you move away from this in target space, that means you're not really sitting at conformal at asymptotic infinity, not knowing the full power or the full dynamics of your space-time. You're not isolating yourself anymore, which is the sense to say, I'm off shell. I'm
Yes.
not sitting. So S matrix means on shell, means you're sitting at asymptotic infinity. Off shell, you're not sitting in the S matrix, you're not computing S matrix, you actually compute the correlation functions, and you can do have access to the full power of your target space. You're not isolating yourself in some region of asymptotic infinity.
Right. Right. No,
Uh,
that's great. That's great. Yeah.
so that's exactly why we need, and that comes to the notion of background independence precisely. And so I appreciate the fact that when people mention or speak and discuss of background independence in GR, they are in a sense, in this sense, in string theory sense, you're talking about off-shell backgrounds, because I don't know how to measure distances.
Exactly. Exactly. You know, you absolutely need that's so the off-shell structure is what gives you the flexibility to think in terms of these background independent notions, because it's like saying it doesn't matter close to what you are, it'll always seem flat. Like in GR,
Yeah,
that's just a statement. You get close enough to something, okay, you're in an isolated region, it's going to be flat. Any force you feel is your sensitivity to the curvature, and that's geodesic deviation. And so here it just manifests itself as saying once you're off shell, right? If you're looking at even the leading deviations from being on shell, which is like one loop beta function, you're immediately sensitive to curvature, which is what we'll see shortly.
exactly. The
Yeah.
concept of a manifold, even in the GR sense, as you move closer to something that looks like flat,
Yeah.
well, it, it
Yeah.
we'll
Let's
see
get to that. Yeah.
exactly. So rather quickly, and the notes here are beautiful. Let's define the beta functions. The beta functions are, you as usual, they're going to be defined with some intrinsic RG scale. This intrinsic RG scale is related, as we're going to see in Zeppelin formalisms, to the UV cutoff of the definer in the world sheet. Just like the subalogically healthy function started with some UV scale, again, or RG scale, this is another UV scale, which is mu, and again, this G mu nu, so this is precisely what we said as A del G of A. Now, our G in the subalogically becomes G mu nu. This was G of A.
Yes.
In the subalogically theorem, now G becomes G mu nu because it's a nonlinear map. And of course, it's not just an A is mu, and of course, it's a function of target space coordinates. So that's the definition of beta function. And as we just said before, our T mu nu is defined as the sum over beta I, and then our marginal couplings. And we know that when this is 0, we have scale invariance, local scale invariance. And so this means O will not vanish. O is not an object that vanishes. So for this to vanish, this means I need my beta functions of the theory to vanish. Cool. Very precise thing. Beta functions are always computed in any quantum field theory to loops in order of loops. 1 loop, 2 loop, 3 loop, beta functions. So because we're doing perturbation theory. And at some point I will so here I need loop order. In this case, it will be order of alpha prime. But I also need, at some point, I'll come to that, which I should have mentioned before, I need what we call RG scheme.
Yes, yes.
Again, this is a subtle point, but we'll come back to it later. Just keep it in mind and ask me next time if I forget to mention it. RG schemes are very important because once we have a beta function, that means I compute it in a particular RG scheme. And this RG scheme will turn out to be is equivalent to what we call field tree definition in target space. Okay.
Right.
So now I'm going to expand my G mu nu again. So I've used this coordinate expansion, normal coordinate, Riemann normal coordinates. And I like that David calls it cunning. Because it really is nice. It does a lot of things, as you just explained. It lands you naturally on covariant objects in target space. You don't have to deal with that. So if I expand, this is just some algebra.
Again, I mean, here's the clear point that this alpha prime expansion is tracking exactly the kind of expansion one would use from purely the geometric standpoint for normal coordinates.
Yes.
Right. So this is exactly the scale at which one will start to feel curvatures if you deviate too much from a geodesic.
Absolutely, because remember, you see, the first order in alpha prime, the first order. Well, this is, remember, as we explained before, this was the second. This was the delta G mu nu, or I'll call this G mu lambda, comma nu k. Basically,
yes, exactly.
derivatives of the metric. 2 derivatives of the metric, and as we just explained, this is proportional by dimensional analysis of alpha prime over RC squared, right?
Yes.
And so the cunning choice of this coordinates already you can see that they're expanding in the metric in covariant objects.
Yes.
R mu nu is a covariant object. This is already a covariant objects, and and I will show you maybe in our paper how this is not what kind of effort this saves you, but because in the fact that you're expanding your couplings in covariant objects right away, and as you mentioned, it starts to feel the curvature of your space-time as you move away from the geodesics, because you can see R mu nu, it's right there. This is the Ricci tensor, the Riemann tensor already.
Exactly.
So, and you can move on in coordinates. But now the chordic order in the fluctuation, we can see that here's the flat space-time piece. That's exactly what you mentioned. So this is the flat space-time piece. So this is the on-shell piece.
Exactly, yeah.
If you will. Polycop on-shell piece, which people are content with. On-shell CFT, I'm not moving, I'm not sensing anything. My full power, my full dynamics of the space-time, right? Move away a little bit to first order in alpha prime, as you can see, and suddenly you see the Riemann tensor, full power of the Riemann tensor and your Riemann normal coordinates. And you can see that's what people call the alpha prime expansion. It's a sigma model expansion, and they call it also a derivative expansion because it's a derivative. It's a number of derivatives or fields, delta mu, delta mu nu. It's a number of derivative expansion. Now it becomes a standard exercise in computing one loop corrections. It's a one loop. And here is the quartic interaction. Maybe next time we'll go into this in a little bit more detail, but maybe not now. But you see,
I mean, basically, we're just Wick's theorem to contract these two.
That's
these
it.
quartic things. Like
it's just an extent. Yeah. It's a standard exercise. I mean, it's not really tricky here or anything else. It's a standard exercise in two-dimensional Feynman diagrams, just Feynman diagrams on the worldsheet. There's nothing really, I would say, tricky about it. And so here is the standard quartic vertex. Here is, and you see that at the vertex, the coupling is basically our, well, it's obvious, right? This is
exactly,
your term, and it's you have k mu to contract it with it. Okay, good. Now you're going to compute one loop diagrams, and of course this is divergent, as usual, loops. So that's why we say beta functions are computed to some loop order. That's what we said here. So in this case, we're going to do it with one loop.
Yeah, he's using the epsilon expansion.
He's using the epsilon expansion, standard
dimensional regularization. Yeah,
the DIN-reg, right? DIN-reg is beautiful. Usually works for lots of different cases. We know that the propagator in string theory is called a free scale propagator. Free string propagator is log of L sigma minus sigma prime squared and with a minus half. This is standard string theory, Polchinski, whatever, standard two-point function, CFTs. Okay. So we need that to compute this object. Now I'm going to, there's going to be, of course, divergences coming from sigma approaching sigma prime, and then we need to regulate and renormalize as usual. Here, David is using DIN-reg with an d plus epsilon expansion, standard stuff. What you get is this integral over k squared, and you'll get something which looks like this: 1 over epsilon. Okay. Okay, so now we need counter terms, just standard story to subtract the 1 over epsilon divergence. Again, you add a counter term, usual story. I'm not gonna, this is just standard perturbative RG. We can find this in any textbook. So you want to subtract the 1 over epsilon the 1 over epsilon divergence. And so you add this counter term. So instead of this, you add this. Oops. You add this term. And then you do a function renormalization. Okay, this is maybe if you guys, well, I don't think we should get into this in a lot of detail. If you like,
sure, yeah,
work it out in detail at some point.
But yeah, I think this should be fairly clear at this point already,
yeah,
because
very clear.
I mean, yeah, the net contribution to the action now comes from this r dy dy, which is of the same shape as the original kinetic term. So we're basically redefining our original g, and then we would take the derivative with respect to epsilon, or log epsilon, and then we would get beta. and
Exactly.
the
That's
requirement
because
that beta function.
dimreg does not have logs. Basically, all the logs in dimreg just like one of epsilons. This is
Exactly. And
so, and that's it.
then,
So there's
yeah,
nothing else here except that when you do this y mu, this wave function renormalization from y mu to y mu, r mu nu y nu, you also well want your coupling, your chi mu nu, to also scale like with 1 over epsilon coming. This guy that has the origin of this is like here. So we have this guy. Again, you're scaling chi mu nu to with r mu nu, exactly as in the wave function renormalization when my mu is actually shifted to 1 over epsilon, alpha prime over epsilon, r mu nu, y nu. Again, same thing for the coupling, again, wave function renormalization. But then the beautiful thing is the beta function, if, well, beautiful now. If you would like your space-time, you remember, we're constructing some space-time that we don't know what it is. We're not saying that this space-time is a black hole space-time or is like anything else. We're just saying it's a space-time with some Ricci scalar and some Ricci curvature and some Riemann tensor, right? And we want it to satisfy Einstein's equation. Okay, so we want r mu nu. Without here, we're not talking about additional T mu nu or anything like that. We're not additional matter, right? So at this point, the condition to satisfy Einstein's equations is that r mu nu is 0. But the beta function we just calculated. Remember, we wanted to start that our theory for quantum. This is a quantum to be conformally invariant because we want CFTs, right? People love CFTs. We want CFTs on the world sheet, which basically means the beta function will vanish. Suddenly, I realized after all this just RG exercise that my beta function is the Ricci tensor.
right.
Oh my God. So for the world sheet theory to be a conformal field theory, and for the target space to be a legitimate string theory background, the Weil invariance condition, Weil consistency conditions, is that the beta functions on the world sheet vanish. It translates to saying that your target space is Ricci flat.
Nice. Yes.
Your target space is Ricci flat, and in this case, without sources. We're not getting any fluxes. We're not saying there are dilatons and others. And so in other words, as David says, the background space-time is which of the string moves must obey Einstein's equations in the vacuum in this case, because again, there are no fluxes here. So if you want without fluxes, if you want to describe a conformal field theory, a string theory background that solves Einstein's equations and defined by conformal field theory on the world sheet, the beta functions of the world sheet, the couplings, become equations of motion, become Einstein's equation of motion. And now, to just give you food for thought, now you can ask, if I give you, for next time, if I give you some nonlinear sigma model on the world sheet, which has not just the G mu nu, has something else. It has the B field, and it has the dilaton, it has something else. And you compute the beta functions using whatever method you like of this two-dimensional interacting field theory, right? Each coupling you add, other than the metric, will have its own beta functions. What do they correspond to in target space? Well, you can say, okay, it's easy to see that there will be some equations of motion for Einstein's theory, but you can ask, what is the action? Where do they come from, right? How can I derive the action in target space?
Yes.
That these equations of the action that has these 7.6 are, as its equation of motion. What is this action, and how do I get it? How do I land on it? And how does it know about the beta functions from the world sheet? There's some action. since we're talking about equations of motion, then there must be some action. And what is this action? How do I get it? And then the story becomes more interesting. And as we add alpha prime expansion and other things, and of course, here we're talking sphere projected to the plane, but you can ask about the torus, higher genus, other things, and what are the implications of this? And there's and the C theorem, is it as straightforward as it was in the 2D case in Mathematica? And then this is probably something we're going to cover in future episodes.
Definitely. I'm very much looking forward to it. But I mean, already here, I feel like this is quite good because I feel like at least I have a little bit more clarity in understanding the point of string theory in general, and also the off-shell form, the importance of the off-shell formalism, sort of in particular. And yeah, I think that but when we keep going, it'll build up nicely to your most recent 2 papers with Aaron. And indeed, I'm keen to discuss more directions to take given that stuff, because I think again, these are things just maybe we could say should have been done a while ago, but
maybe should have been done. And there's actually something that will connect off-shell string theory in the bulk to TT bar.
Yes. We will definitely get to that. Yeah.
Because if I select the space-time in the bulk, a state that doesn't solve Einstein's equation, a state in the bulk, then what does it correspond to on the boundary?
Right.
What the CFT is not it's not a state in a CFT anymore. It's just I think it's going to connect to TT bar actually.
Well, I mean, I would even be a little bit more direct with it, is to say that that the equations coming from TT bar just encapsulate constraint equations, and there's a slightly different status of constraint equations as compared to equations of motion. You see, there's a sense in which they subsume a subset of the equations of motion, right? Constraints subsume in general relativity a subset of the equations of motion.
Yeah.
But those their action is encapsulated essentially by things we've presupposed, that it's a diffeomorphism invariance that we've kind of presupposed in the entire construction.
Yes.
Right. So in the off-shell formalism, we should be able to go between these two things, right? We should be able to give meaning to just the constraint equations in isolation of going on shell completely, right? Sort of setting aside that problem. Right. And that would be the route I would pursue, to just directly capture what the TT bar equations mean from this off-shell perspective, because they aren't necessarily coming from taking the on-shell condition of truly setting beta to 0, which again is subtle, as you mentioned, because of scheme dependence issues. Now, what does scheme dependence tell you? It tells you, well, I could take maybe beta and then redefine it by beta mu nu goes to beta mu nu plus symmetrized derivative of some x nu, right?
Yes, absolutely.
Now,
so I see. So the TT bar, from the TT bar, because you have constraint equations, and these constraint equations, I would have thought, maybe this is for some other time, but I also thought that the constraint equations in the TT bar are equivalent to the Weil, what we call in the sigma model, that the Weil consistency equations are equal to equations of motion. Somehow, if you violate the constraint equations, you're going away from this. You're violating the Weil.
Well, the thing is,
the sacred rule. The Weil consistency conditions are equal to equations of motion, and so on and so forth.
Yeah, so definitely. So Wess-Zumino consistency conditions of the local RG of the boundary theory give rise to the TT bar flow equations essentially. But now there's a subtlety, because the target space is kind of somewhere in the mist in this entire discussion. So it's sort of unclear.
All boundary, right? This is all boundary.
Yeah. This is all sort of boundary consistency conditions. Now, from the target space itself, there's a very clear meaning to that geometric connection as well, right? Because we have this clear picture of what you have basically pick a boundary, right? Either pick a boundary or pick a Cauchy slice, depending on the variant of this you want to pursue. Now ask, what are normal and tangential deformations of this boundary? Those normal and tangential deformations are essentially captured by the constraint equations. Right? So that's the kind of
Yes.
thing that you'd have to do. You'd basically have to say, well, you see, it's really coming from, in my opinion, a subset of these scheme dependencies or scheme independence itself. Right? It's not necessarily coming from just taking, so basically where the constraint equations sit in this story will give you the answer. So you need the off-shell formalisms so as to be able to say, let me only impose constraints and not the rest.
I see. Just
Okay?
constraints.
And that will basically tell you, or that will basically tell us exactly what the role of this TT bar is from the
bulk
from basically the worldsheet perspective, the sort of sigma model perspective. And I don't think that this is a matter of new there's no new calculation that needs to be done here, in my opinion. I think we're almost at a state, with this understanding of how to construct the off-shell action and so on, to basically pose this question, right? So basically starting from the one loop approximation, where we expect that you just have Einstein-Hilbert-like dynamics, ask what is the role to be played by these constraint equations, right? The constraint equations in a situation where you actually have finite space-time volume.
Okay, good.
Which is good anyway, right? From
yes,
sigma model perspective,
absolutely.
that's good anyway.
Absolutely.
So finite space-time volume, what happens? I just want to know, how does my action on shell respond when I change the space-time volume by moving basically by moving the wall, right? Say that this was like manifold with boundary. I'm just moving this now. What the status of this wall is, how it comes into, like, where does it come from the full string perspective? Is it something you do with Hoshaba, Witten, whatever? Set that aside, right? We have, just look at this configuration. So we have like a sigma model, and the sigma model takes as target some space with a finite volume, right? You can either realize this as a compact space, or you could realize this as some non-compact space, but with boundary, right? And in this latter case, how does the action respond when I change it's like changing the location of this boundary, but covariantly that means when I change the volume. Should be completely answerable question.
Yes, it should be.
Right? And it'll immediately tell us how alpha prime corrections manifest in this TT bar story.
Yes, I guess that's the most concrete question to ask.
Exactly.
In the sense, if we imagine, so the setup here is, imagine you have a string theory, it's sitting in the bulk.
Yes, exactly.
Rather than any other theory phonogram. So you have a string theory sitting in the bulk, right? So that's the thing. And the string theory in the bulk, you have a world sheet and you have a target space in the bulk. Usually that's the beauty of this ADS3 CFT2 sort of NS formalisms, where you have the world sheet and the target space in the bulk, right? So you have a world sheet sigma model in the bulk or theory, and you have also target space, your actual bulk, your actual target space bulk. And then you have a CFT, two-dimensional 2D CFT, that is TT barred, and you ask the TT flow equations or the constraint equations, how that takes you a finite distance into the bulk. What do they correspond to from the string theory sitting in the sigma model, in the sense of alpha prime expansion or off shell? Because obviously they take you away from the CFT. So definitely they should correspond to something that takes you also away from the world sheet CFT. I think naively, at least.
Definitely. No, it definitely does. I mean, there's the brute force thing. You just try to compute the TT bar deformation of known world sheet theory. But I think that the more important or subtle thing is to understand that we know what the role is of constraint equations in the bulk, right? That's not. Now, all we're doing is saying we're going to change the volume. We're going to change the volume. How does my action respond?
Yeah.
Should be doable. Should be doable.
Very doable.
And basically the deformation will come out as a result. It won't be the input. I think the principled way to do it would be to see that this deformations, whatever the deformations of the world sheet theory are, TT bar and more, will come out as a result, as a consequence. This would be not as an input. I mean, it won't obviously just be TT bar of the world sheet. That's not what's not gonna happen. I mean, it's gonna be TT bar of the boundary theory, but
Boundary, exactly.
of the world sheet, it's something. That's the result that we need to see come out.
You see,
And I
that's the
think that
beauty. If you take one of these recent results about exact conformal, these papers by Lorenz, Gabriel, and Gopal Kumar, where they have, for example, deriving ADS3,
yeah,
deriving the ADS33, where they have the actually in some approximation where they have the endpoint functions, right? Um, Endpoint functions of the boundary CFT is
yeah,
equal to the endpoint functions of the CFT vertex operated world sheet CFT correlates. It's an
exactly.
equality. So, well,
The
if you take
attention is
this, then deform your boundary CFT, it's an equality. Then the TT bar deformation on the boundary CFT corresponds to a TT bar like deformation in the world sheet CFT, at least in that example.
so I think that the important exactly. So what happens is that when we try to play these games and when we try to go to like these other models where you have something a lot more than just Einstein gravity happening in the bulk, there the issue is you need to expand you have to have a huge sentence of deformations in addition to TT bar to really get this to work, and it's worth doing. Now there's probably a more parsimonious way of figuring it out, which is to go to the sort of invariant statement about sigma model. Sigma model has whatever, like sigma model has metric, it has B field, it has everybody, right? Question is but okay, I'm still doing this, guys, just take this sphere, but like when I move the walls, what's happening?
Yeah, good.
Right. So that if we can answer that question, then we have a good handle on knowing what to do. Now that the subtlety is that it's a slight generalization beyond. Well, I don't know. I mean, with negative cosmological constant, you just have, well, you have the asymptotic boundary, of course.
Sure.
But if you could have negative cosmological constant and volume of your choosing, meaning you have a boundary which is now right? Now, that's the context that I think one should start with and then just work out. Because this thing being the boundary, right? Like, that's a sort of, again, a non-shell statement. You need to know the solution to say, oh, there's a boundary here. Really, what you should be able to do is integrate the equations of motion away from that, all the way into the center, and say, oh, look, this actually came so this is why the constraint equations aren't even telling you what happens entirely, right? They're kind of not the full on-shell information. So from that perspective, like that's why I was trying to like delineate these questions a little bit carefully, because I think that this is something we could almost certainly do. And again, to the listeners, if you have any ideas, send either of us emails. If you've gotten this far, if you've gotten this far, definitely like, share, comment, subscribe to the channel if you haven't. Presumably, we should stop at least the recording for the time being.
Absolutely.
But check us out, Theoretically Podcasting, and specifically the Sigma Model Chronicles will be continued.
Absolutely. It will. Yes, it will.
Yeah. Thank you.